Okay. So good morning, everybody. Thanks again for coming today. Very happy Christmas to everybody in advance. If Amicha is watching, and Merry Christmas to him too. Right. And may God give everybody good wisdom on this day. So okay. Yesterday I talked about these rotation generators, right? And so I've given you some background on group theory, right? Just minimum background, just enough to sort of like tell you what a group is and so on. And so what sort of group is this? So SO3 is the group of rotations, right? What does this SO3 mean? What does S mean? Anybody? What is S? Huh? So S is what? Special. What does that mean?
Modulus 1.
Modulus meaning what? What do you mean modulus? Modulus of what?
Determinant of A is equal.
Right. Determinant is 1. Right. What is O?
Orthogonal.
Orthogonal. Okay. Which means what?
A transpose.
A transpose equal to A inverse.
Right. And what about 3?
Three by 3.
What? 3 by 3 matrices, right? Real or complex?
Real, sir.
Real. We have not specified it, so it's real. Otherwise, if you want to be very careful about it, you would say SO3R, but it's fine. It's just, you can just say SO3. Okay. Now this orthogonality condition, by the way, what does it mean, right? It means that if you look at this group, if you look at some matrix, which is some member of this group, then, or more precisely, again, I should say, which is an element of one representation of this group. Okay. So groups, I've told you that group elements are abstract objects, right? So we pick a vector space on which the group will act, right? So in our case, what is that vector space? Vipul? SO3 will act on which vector space?
JX, JY, JZ?
No, R3. The set of
Yes, sir.
vectors in R3, na? X, Y, Z.
Yes, sir.
Right? And then we say that it is on this vector space, the representation of SO3 on this vector space is given by 3 by 3 matrices. Okay. So now the thing is that you can have other representations of the same group. This representation This is called the fundamental representation. Okay, it corresponds to J is equal to 1, where J is the spin. So J is some spin angular momentum, right? Now, so you can have J is equal to 2, 3, 4. For depending on the value of J, you will get a different dimension. Now, the dimension of your representation matrices is equal to 2J plus 1. So for J is equal to 1, what is the dimension? 3. But if you take for J is equal to 2, your dimension will be 5. So if you have this J is equal to 2 representation, you will be working with 5 by 5 matrices. Okay. So we say that it is SO3. Okay. But the 3 refers to the fundamental representation. Now, all of these things may not be very clear to you at this point, but that's okay. The terminology is also important, right? Just understanding what the various words mean. There is a lot of, right? Whenever you learn some subject, there is always a new dictionary, right? So that there are a lot of new terms like representation, fundamental representation, dimension, spin, action of the group, right? On which vector space it acts and so on. So you are introduced to all of these new terms. Then over time you understand, okay, why these terms make sense. Okay, so it's okay if you don't understand everything immediately. Don't worry about it. Just try to take the minimum information, which is that SO3 is the group is given by 3 by 3 matrices. Okay, you can think of all of this as extra information.
Sir, J is also changed, no?
Huh?
J matrix is also changed, na? J for J.
Bilkul. Absolutely. So exactly. So J. So what is J? J is the generator of rotations. So if you change the representation, right? Your rotation matrix, if it becomes 5-dimensional, then your generator will also have to be a 5-dimensional matrix. Okay.
Yes, sir.
Hello, Nishita. Good morning.
Good morning, sir.
I think it's important to say good morning to you because out of so many people, there are like only 2 ladies in my class so far, Nishita and Aditi. And it must, well, you know, you have to respect that. Okay. So for this group, right, we have these generators. Now, what is the meaning of a generator? Generator means that you have something, okay, some matrix or some object, and then you take the exponential of this generator, okay, and there are some constants or something, and this gives you the group element. Okay, so as an example, if you take this exponent of minus I, let's say theta jx by h bar, this will give you rx theta, the matrix which gives you rotations around the x-axis, or more correctly in the yz plane. So this is the relationship between generators and group elements. So generators are also matrices, group elements are also matrices, right? But one is given by the exponentiation of the other. Okay. All right. Now, so today I'll talk about something that is I had shared this PDF with you yesterday, right? So now we have these angular momentum operators that we have discussed earlier. Right? Lx, Ly, and Lz, where this L is equal to R cross P, right? So for instance, Lx is equal to IH bar Y times dou Z, Z times dou Y, right? So which is equal to Y PZ, ZPY operators, right? So what is the relationship between these operators and, for instance, these J's? Okay, so that is what we want to try and understand today. And what is the effect of these operators? How do they act on quantum states? Okay, now let's say that you have some state. Okay, you have some state psi. Now you remember that this state can be written in some basis, some position basis, let's say, right? So if you were in one dimension, how would you write it? You would write it like this, right? In 1D position basis. These are the position eigenstates. Right? But we want to talk about states in 3 dimensions, right? States of some, for example, state of an electron in a hydrogen atom. It's something that is in 3 dimensions. So in 3D, your position eigenstates, your position operator is this R hat. I'll put a hat on it, but it's not a unit vector, right? This is the operator R. With eigenstates, what are going to be the eigenstates? So I should call this vector R hat. This is a little bit of a complicated notation, but you know. And please let me know if at any point my audio or video is not coming through, okay? Because my network is a little unreliable these days. So if you have a state in 3 dimensions, how will I write it? Yes? Pranav? Shantanu? What will be the next thing after this integral?
D2.
Huh? D?
R.
D2. dr cube per. Sorry, d cube of
D
r.
cubed R. Right. And
Psi R.
psi of vector R, right? And ket R. Okay. So this is exactly the same by analogy with your one-dimensional case. So now, okay. So let me write that one more time. I will need that expression here. D cubed R psi xyz, let's say. Okay. Or I will keep it as psi R ket R. Okay. Now, if I want to, so what is this psi of R? This is the component of R of psi, right? This is the component of R along the vector, which is given by this, right? So if if I take this, if I do this, let me put a prime here on this R. Okay, sorry about that. Let me put a prime here on this R. By the way, do you guys have a class at 9? Just asking.
No, sir.
No? Okay, okay. So I'm going to take some time. Okay?
9:30.
So 9:30. Okay, I'll finish by 9:15. So this, okay, I'll write it as R prime. It doesn't matter, right? I can call it anything. Now I take ket R and I take this inner product. Okay? What will this give me? D cubed R prime, psi I R prime, then ket of R prime like this, right? Is this fine? I hope everybody is following this. If you're not following this for any reason, you please raise your hand or say something, okay? How many of you are following this? Raise your hand. In the participants window.
Sir, why not dr instead of d cube r?
एक सेकेंड अभी बताता है. Okay, so there are some of you who are not so confident, right? So let me. That's why I'm asking. Na, that tell me if you have any doubts.
Sir, like,
right?
why are we taking R dash? Like, what's the
So you can call it anything. Na, you can call it this thing. I can call it R. I can call it. Okay, thanks, guys. That gives me an idea now. So see. Instead of R, I can call it any. I mean, what it means is, this is just I'm performing an integral over this R na, over this variable. Here there is an integral, right?
Yes, sir.
So this is a dummy variable, right? Whenever I have a sum over something or an integral over something, that's a dummy variable, right? So if I sum over f of xi, let's say, I can also write as sum over j of xj, right? It's the same thing, na?
Yes, sir.
ठीक है ना? So instead of writing d cubed r, I can write d cubed r prime. It doesn't matter, right? It is just a dummy variable. Because the integral will not depend on r or r prime, na? The net result of the integration will not depend on what I use. Or, okay, if it makes you feel comfortable, let me just use r. Okay? Is this better? Is this seem more natural to you?
Yes, sir.
चलो ठीक है. Now let me take one ket r prime and take this inner product. ठीक है, now it's fine.
Yes, sir.
Acha, what was the question that Vipul was asking, by the way? Why
not dr, sir?
Well, you mean like this, D vector R like this?
Yes, sir. You
Well, it's the
put
same
a
thing,
d
na?
cube r.
Whether I write this or d cubed r or r square sine square theta dr d theta d phi. Matlab, this notation means the same thing, na? Right? See, if I write d vector r, I mean dx dy dz, na?
Yes, sir. I know.
I mean, okay, maybe, and actually no, they don't mean the same thing. What is dr? Dr is a vector. So this is r plus delta r, and this is dr. So if you do the line integral, right, of something, then you would say a dot dr. if you take the line integral of something along some curve, right, then you would say A dot dr. So this would be dr. But here we are doing a volume integral, right? So it's d cubed r. So d cubed
Okay,
r is like the same as saying dx, dy, dz, or by saying dv. It's all the same thing. Okay.
yes, sir.
Okay. Now when I take this inner product, what do I get on the right side? D cubed r psi r del cubed r minus r prime, right? Because these states are orthogonal to each other, right? And I get a Dirac delta function. So when I perform the integral, what will I get? I will get psi of r prime. All right. I think people have like forgotten, a little bit out of touch. People are feeling. So by the way, I'll open up this Moodle page for homework 6. So please submit homework 6. Okay. I'm sure everybody has done it. So you can submit it by today. Okay, na? And then I'll start giving you problems for homework 7. I think when you have problems, then your mind works better. So see, Shantanu, this is why I was writing r prime over here, so that here I could get r. Okay, it doesn't matter. So if I say r psi, I get psi of this r. I get the component psi r. Okay, that's all I'm saying. Is this making sense to you all?
Actually, sir, like the problem is like I am unable to comprehend like where we are going with this. Like for the last 1 or 2 lectures and this, like where are we going with this? Kind of you get my concern what it is.
Ah, okay. So where we are going with this is we are okay. Today, I think you will understand if you bear with me. If you have a little bit more patience, I think today you will see where we are going.
Okay, sir.
I mean, it's a fair question. Sometimes some things just take a little bit of time to become clear, right?
Yes, sir.
Okay. So now I think it will become clear at this point. So now you are working in some set of coordinates, right? X, Y, Z. You have some set of coordinates in which you are defining this psi of r, right? Okay, this is your vector r. At this point, you have psi of r, which is the component of psi at that point, right? Now imagine that you perform a rotation of your coordinate basis. Okay. So you perform some rotation, some r matrix of your coordinate basis. Then what will happen? You will take any vector, right? Or let me write a vector r. You will take any vector r to something else, to r prime, let's say. Right? You're performing a change of basis. Okay.
Yes,
Now,
sir.
when you perform this change of basis, what happens to psi? This is what we're trying to understand. What happens to psi of r? Okay. So under this rotation, what will happen to this ket? This ket will go to r prime, which is what? This thing. Okay. R prime is matrix R acting on the vector R. Now, the thing is that this state, the whole state, which I write like this, this state should remain unchanged under this rotation. Okay. So if I perform this rotation in the new coordinates, what will the expression for the state be? The volume element will not change, right? This is d cubed r. Under a rotation, the volume element does not changes. No, right? Because this is because the rotation matrices are orthogonal. Okay. So what will happen? These components will change. You'll get some psi prime r prime and ket of r prime. This is the state in the new coordinate system. Now, what is this r prime? R prime can be written as some matrix R acting on vector R. Okay. What about this psi prime r prime? What is this r prime again? This is psi prime matrix R acting on R. Okay. But now the thing is, see, when I perform this rotation, what happens? This vector R goes into some new vector R prime. Okay. Under this rotation. And whatever is the value of psi of R over here, that becomes the new value of psi prime R prime here, right? Okay, you are just taking everything and rotating it. So psi of R is some function of R. So at the new, when I rotate it, I get some new function of R. But the value of the function at the rotated point has to be the same as the value of the function at the old point. So what I can do is I can write this psi prime R prime as psi of R inverse R prime. What does this mean? The value of this function at the new point is equal to the value of the old function at the old point. Okay. Now, so what is going on, right? So we have some state psi. So under the effect of the rotation, it should undergo a change. It will undergo some change and it will become a different state where R is some operator. This operator acts on the old state to give us the new state. So I guess I should not say that the state remains the same. See, one way to understand this is imagine you have some function f of x, y, z. Okay? I can write that as f of r. Now I perform a rotation of my basis, right? So that means every vector r is changed into some vector r prime. Okay. Now what does this do? So imagine, let's say that your function looks like this. Okay, let's say your function looks like this. This is like a p wave, right? You remember from, so this is f of r. Okay, just to give you a schematic diagram. Under the rotation, what will happen? Under the rotation, let's say it will look like this. Right? Now, what is this? This is F prime, R prime. Okay. See, if you look at a simpler example in one dimension, let's say you are in one dimension, you have x and f of x. Your f of x looks like this. Now I perform a translation of the x coordinate. Okay, so I perform a translation. X goes to x prime is equal to x minus c. What will happen to my function?
Just shifted,
my function will be shifted now. By what amount? By an amount c. Right? So f of x prime will be equal to what? F of x minus c, right? Okay, na? So it is exactly the same thing is happening. F of r prime is equal to f of this matrix R acting on R, right? This is your transform coordinate. Now, I want to ask what is the effect of this transformation. So this transformation, what would I do? Once I say that this is equal to f of x minus c, now I would use some sort of Taylor series. I would write it like this, right? Okay. This is the Taylor series expansion of this f. Is this you have seen this before, right?
Yes.
आप लोगों को ये समझ में आ रहा है? This point, this much is clear.
Yes, sir.
Yes, sir.
Now this expression can be written as exponential minus I by h bar c times operator px acting on f of x. Does this step make sense to you?
Yes, sir.
ठीक है ना?
Yes,
px
sir.
is what? Px is I h bar d by dx, na? So h bar will cancel. I will also give you minus 1, that will cancel. So this exponential will just become c times d by dx, right? When you expand this exponential, you will get exactly this Taylor series. We'll put a minus sign there. Okay, so that is exactly what I'm trying to understand, how to do that for rotations. So this is f of r prime, which is some rotation of this r. Okay, I want to write this as f of r plus some small change delta r. Just the same way that I wrote this translation as some small number c. Well, I didn't say that c is a small number, but let's assume that it's a small number. Okay. So what should be the form of this delta r? Okay. Now let's see this. Let's say that let r be rz d theta. That means a small rotation around the z axis or in the xy plane. Okay. So what is this R of Z d theta? What does it do? What does the matrix look like? Cosine d theta, okay? Then minus sine d theta. I think I was making a mistake with my sign. I think there should be a minus sign here. Then sine d theta and cosine d theta. 0, 0, 0, 0, 1. This is going to be my R matrix, right? For rotation in the xy plane. What will be the effect of this rotation on a vector? Let's say x, y, z. So this I can write as, when you take the limit of small d theta, I can write this as 1 minus d theta, 0, d theta, 1.
Sir, your voice is gone.
Now I'm back. Okay? Can you see me now?
Yes, sir.
Yes, sir.
So what is the effect of this? Let's see, 1 minus d theta, 0, d theta, 1, 0, 0, 0, 1. You are understanding now how these steps, I hope. R, Z, d theta is this. Then I'm taking the since d theta is some small number. Okay? I can write cosine as 1 and sine theta is approximately theta. So this thing acts on x, y, z. So what do I get? You multiply this, you get x. The first term becomes x minus y d theta. The second term becomes y plus x d theta. And the third term becomes z. Okay? Is this fine? So
Yes.
psi of r prime, this is r prime. Psi of r prime is equal to what? Psi of x minus y d theta, y plus x d theta, and z. Okay? This is just r prime. Okay? Now let me perform a Taylor series. So let me remind you how to do a Taylor series for a multiple function. Let's say you have x plus delta x and y plus delta y and z plus delta z. How do you write the Taylor series expansion? You write it as psi of xyz plus delta x psi xyz plus delta y xyz, right? Plus delta z. But here you have to take the derivatives, right? In the next term, you have to take this derivative. Now this derivative has to be what? Therefore, delta x, it has to be d psi by dx. This has to be d psi by dy. This has to be d psi by dz. Right? This is the Taylor series expansion for a function of more than one variable. Okay? Is this point clear?
Yes, sir.
Okay, na? Now I'm just doing the Taylor series expansion. So when you look at the term associated with x, you have to take the derivative of psi with respect to x. When you look at higher order terms, you will get you will get dx, dy, dz and all that, but we are not concerned with that. Okay? So now let me take this function and Taylor expand it in this way. Okay, this is the function. Now I'm going to Taylor expand it. So the first term will become psi xyz. The second term is minus y d theta, that is your delta x, right? D psi by dx. This is delta x, right? Then you will get x d theta d psi by dy. What is this? This is delta y. And then you will get higher order terms. Order the d theta squared. For z, there is no change, so I don't have any term corresponding to z. Okay. Now what is this? This can be written as psi xyz. I will collect the d theta. D theta is common in these terms. I will collect that. Okay. And now you see, I can write this as x dy minus y dx acting on psi. Do you see this or not?
Yes, sir.
Huh?
Yes, sir.
ठीक है ना? What is this expression? X dy minus y dx. What is this? You recognize this expression?
LZ.
It is equal to LZ, right? It's equal to LZ divided by h bar times minus I. Right? So this means that psi of r prime is equal to psi r minus I d theta LZ by h prime psi. Okay. What do you think the next term in this expansion will be? Any guesses? Right? The next term will be what? It will be minus d theta squared by h bar square LZ squared psi. What can I write this expression as? This whole series, what do you think, what form will it take if I want to write a compact expression?
Exponential.
Exponential form.
Exponential what? Minus I by h bar d theta. D theta is the amount that which I am rotating by, right? LZ acting on psi. Okay.
Yes, sir.
So what is the meaning of this LZ now? What is LZ doing?
Generator of rotation.
It is the generator of rotation. Thank you very much. Do you understand now the relationship between angular momentum and rotations?
Yes, sir.
What is that relationship if you have to state it in one sentence? Yash?
So when
Huh?
so it is causing a rotation in XY plane by operating the LZ.
So if you want to make the statement precisely, the angular momentum operator, right,
Yes.
is the generator of rotation.
Yes.
The same way that the linear momentum operator is the generator of
Translation.
translation. Shantanu, now can you see where we have been going past two lectures?
Yes,
Sort
sir.
of, maybe. कुछ आपको मतलब idea मिला?
Yes, sir. Yes, sir. We were trying to create an analogy between translation and rotation and momentum and angular momentum.
Angular momentum. But we were trying to understand the physical effect of this. Okay.
Yes, sir.
Now see, now we can get rid of this. This is an infinitesimal parameter, right? Here d theta is much less than 1, let's say. But now I can write for finite theta, psi of r prime is equal to exponent minus I by h bar theta Lz psi of r. Okay. Why can I do this? Because I just keep multiplying, I just keep acting with many copies of this. So I keep doing the rotation by d theta, d theta, d theta, d theta until I get to until all of those small d thetas add up to one big theta, right? So I can write, for example, d theta as your finite theta by n, where n is some number much greater than 1. Then exponent of minus I by h bar theta Lz can be written as exponent of minus I by h bar d theta times Lz to the nth power. Right? So when you take exponent of something x to the nth power, what do you get? You get exponent of what? Nx, right? Now, Lz is an operator, but if I write exponent of minus I a times Lz and multiplied by exponent of minus I b times Lz, what is the answer? Exponent of minus I times a plus b Lz, right? Because Lz commutes with itself, no? There is no issue with commutation. So I can generate any finite rotation in this way. What about thing? What about Lx and Ly? So similarly, if I want to generate a rotation around y by some angle, so now I will use this angle Rx. Let's say I want to generate Rx, I will write theta x, okay? Ry, theta y, Rz, theta z. So how do I create a general element? I do exponent of minus I by h bar theta x Lx, theta y Ly, theta z Lz. This gives me a general rotation. Okay. This means that I am rotating around Lx by theta x, right? This is what it means. Another way to write the same thing is exponent of minus I by h bar one constant number theta times some unit vector L dotted with the operator L. So what is the meaning of this? Any rotation in 3 dimensions can be written as, so you have some vector R to perform some rotation, okay? This rotation can always be written, you can take some unit vector n hat and you can say that you are rotating around this unit vector n hat by some angle theta. So this is a general property of rotation. So that is what this expresses. This tells you that you can generate any rotation in this way. Okay. Now the thing is that this tells me what are these operators. So angular momentum operator generates rotations, and these angular momentum operators, you know what they are. Li is equal to, so Lx is equal to minus I by h bar, y dou z, z dou y, and then cyclic permutations. Okay, and then you can show that if you look at the commutation relation of Li and Lz, you get I exponent ijk Lk. So this you should prove. Okay. Homework number 7.
So we have done this in the homework 6.
अच्छा चलो ठीक है, फिर से कर लेना एक बार. ठीक है, if you have done this, fine. Okay, then what about this? L square comma Li is equal to 0. Have you shown this also in
Yes,
homework
sir.
6?
Yes, sir. Yes, sir.
Yes, sir.
ये भी हो गया क्या?
Yes, sir.
अरे यार आप लोग तो बहुत ही मतलब diligent students हैं. ठीक है? Now the question is, what is the relationship between all of this and this Jx and Jy and Jz? You're right? आपको याद होगा कि हमने ये Jx, Jy, Jz डिफाइन किए थे ना, तो उनका क्या रिलेशनशिप? व्हाट इज द रिलेशनशिप बिटवीन दोस Jx's and this angular momentum? So Jx we had defined as 0, 0, 0, 0, 0, minus 1, 0, 1, 0, right? Something like this, with some constant coefficient, whether I or something like that. What did this give us? This gave us, if I took exponent of minus I, again minus I by h bar Jx, theta Jx, what would this give me? This would give me Rx theta. Rx theta is the matrix 1, 0, 0, 0 cosine theta minus sine theta, 0 sine theta and cosine theta. Okay. So this matrix, what is it doing? It takes the vector R and rotates it to R prime. So if I take R and act on this vector with Rx theta, I get R prime. At the same time, if you look at the function psi of R, right? How does the function psi of R change? The function psi of R becomes so exponent minus I by h bar theta times Lx. Put this on a new line. Okay. So what do these Jx's do? These Jx's, they generate elements of the rotation group. right? And that element of the rotation group takes my vector into the new vector. What do the LXs do? LXs, they also generate rotations, but they act on functions. Okay. So LX and JX, they both work together. JX transforms the vector, LX transforms the function. Let's see. Right now for understanding more of this rotation group. If you can understand what I have explained today in class, I think that is probably good enough. So please try and digest this over Christmas. Okay. I think this is enough information for one class. So you have to sit down and work through this. Okay, you have to work through these manipulations yourself to understand what is going on. Okay. Question.
Sir, sir, whether JX and LX are both are same, or is there any mathematical relation between those two?
So they are doing the same thing. Okay. So JX is generating a matrix, a rotation matrix, right?
Yes, sir.
JX, if I exponentiate JX, I get a rotation matrix. Okay. If
Yes,
I
sir.
exponentiate LX, right, I don't get a matrix, right? I get a transformation which changes this function. Right. So one of these has the effect of transforming the vector, and the other one transforms the function. Now, so they both act, I mean, both of them correspond to the same physical transformation, which is a rotation. But the vector has to transform in one way and the function has to transform in a different way. Right? I cannot use JX to transform this function, because this function is a scalar quantity, no? JX is a matrix. The matrix cannot change the scalar quantity.
Yes, sir.
Okay. Now, if you consider, for instance, the state of a spin particle, if you consider a spin 1/2 particle, right? In that case, your state will be given by some matrix, like 0, 0, 0, 1, 1, 0, that kind of matrix, right?
Yes, sir.
In that case, what will happen is the action of this will be given by this something which is related to, then
JX.
that state will transform under the appropriate JX. In that case, it will be sigma X, the Pauli matrix, the 2x2 Pauli matrix, which is just this component.
Okay, sir.
Well, actually, it will be, this is not sigma X exactly, but.
Okay, sir.
Sigma
Thank
x
you.
is 1, 1. So this is sigma y, right? This will give you. So again, I mean, for some people, I might be going too fast. For some people, I might be going too slow. I don't know. It's hard to tell because there is variation. So anyways, I'll stop the recording.